Hello, my name is Timothy, and today I'm going to talk about adaptation of ISP for computer vision. I'd like to introduce our company first, and then talk about ISP and exposure control, and using ISP for imaging data augmentation and adaptation of wide-angle solution for computer vision. So first about our company, Pony AI. We are a startup. We have two headquarters, one in China, one in United States. Recently, we launched a fleet of 100 cars in Shanghai, and we're expanding operation in different cities in California as well. We build all our core technology software in-house, and for the hardware, we partner with OEMs and hardware manufacturers. And one of the partnership, which I'm going to highlight today, is the partnership with ON Semiconductor, a global leader in image sensor and ISP for autonomous vehicles. First, I'd like to talk about exposure control in photography and automotive. In photography, we have aperture control, ISO or gain, and shutter speed or exposure time. And in automotive, we don't have moving parts in the lens, so the aperture is fixed, and we can only control the shutter speed and the gain. Usually, the shutter speed or exposure time is changed first, and when it reaches maximum time, then the gain is applied to compensate for the dark image to reach the target value. To tune exposure control properly, it should be limited to avoid motion blur, and the gain should be limited to avoid maximum noise, to limit maximum noise level. Also, we should adjust the target of the exposure for each zone, and also set the metrics for metering to set which area is important for us and which is less important. And then when the exposure control is properly tuned in the field and in the lab, we apply different ISP settings for each pair of gain and exposure control. Here is an experiment in the lab using onsemi 231 sensor and a P200 ISP. We applied manually different exposure times to our scene, which consists of some charts, a moving object, some small model of the cars, and other objects. So first, you can see short exposure time and gradually increase to a longer exposure time. And looking into the zooming up into some cropped regions, we can see that long exposure produced a lot of motion blur. The object is hardly detectable. In the short exposure, the object is too dark, and like middle one is quite acceptable. As for human vision chart, it got overexposed in the long exposure, and the short exposures look like okay. Some cars are located in the bright area near the light, and they are nearly oversaturated in the long exposure, and in the short exposure they are too dark, so the middle ones look fine. But in the shadow area, only the long exposure showed some good results. So summing it all up, none of the exposure settings are good for all the objects. So the exposure control, automatic exposure control, tries to optimize the camera exposure for the whole scene, and we never can get optimal settings for each of the cars in the scene. Same outside, where the dynamic range is much wider, we can see that the long exposure produced a blurry scene, even though the noise is not noticeable, but the image is not sharp. And as for the short exposure with a high gain, sharper image, but the noise is quite noticeable. And which of the two settings will be better for the whole training set is a big question, because once we train on one setting, we get one results, then we add more images or change the model, change the parameters, everything can change. So it's very hard to extrapolate to data which we have never seen. So the only data-driven solution would be to provide both of those images to the network by capturing them in different environments. But if your fleet is not that large, what we came up as a solution is to capture them sequentially using different exposure augmentation. So conventional augmentation approach is collecting training data and then applying different modifications like contrast, adding noise, rotating the image, adding some geometrical transformation. And what we do is we change the settings of the ISP by controlling the exposure time during the collection stage. So we are synthesizing collection and augmentation stages in one stage. Google Brain paper talks about applying different augmentation policies and how they improve the training process. We can achieve high precision on much less data if the augmentation policy is applied. And what we propose is not applying the modification to captured images, but just applying it to some of the images in our image stream. So we separate the image train into anchor frames, and the frames in between will be altered by changing the exposure time. Here is an example on the same scene. By manually changing exposure time, some anchor frames are fixed, and in between we have a longer exposure time, shorter exposure time, and we have different versions of the same car with oversaturation, with a dark setting, automatically produced by the ISP. And here is the demo on our camera in the car. We can see the noisy image. We also can apply the same idea to white balance and change white balance gains to apply for wrong color temperature detection in the ISP pipeline. Here I'd like to show the dynamic range chart and see how the noise profile changes when we change the exposure time. So when we change the exposure time from like 2 milliseconds to 12 milliseconds, we see that the noisy patch moves from this patch to this patch and vice versa when we sweep the exposure. So why I capture this is to point out that if we apply, for example, if we add noise to this image, we will be nothing close to this. Or if we adjust the levels, which I actually did, so this is like 8 milliseconds, which is brighter image, and I reduced the levels and added noise, and Gaussian noise was added to all patches equally, while since the noise function is a square root of the signal level, it has a very sophisticated profile when it goes through the tone mapping and other blocks like gamma and ISP. So reverse is also doesn't work. When we adjust the level of 2 milliseconds and make it brighter, it doesn't look like a 8 millisecond image. That's why software augmentation fundamentally is not correct, and it's not following the actual process in the sensor, how the noise is built. So comparing the hardware and post-processing augmentation, the fundamental difference is that in ISP augmentation, we actually model the physical process and change the data on the capturing stage. On the other hand, we can't do any kind of geometrical transformation, occlusion, and stuff like this. So we have to combine both of them to reach maximum efficiency of the training process. And as you notice, the stream that I have shown was captured by wide-angle camera with 180 horizontal field of view, which has some image circle and also distortion in the periphery of the image. So usually wide angle is not used in automotive because the MTF and the sharpness chromatic aberrations degrade in the corners of the image, and it's very hard to project the lighter depth points to the back to the image for the sensor fusion because of the lens and how it's made. So what we propose here is a solution which we done also together with on semiconductor and the wide angle lens designer called Immervision, Canadian startup. So here you can see the lens of Immervision and attached to the prototype development board. And what Immervision lens does, it actually stretches the periphery of the image by special lens design. So more pixels per degree are projected to the side of the image. And then special correction in ISP is applied to put it back to compensate the distortion for this lens specifically. And when the shrinking is done, the MTF is reconstructed. So the image is sharp and crisp at the corners, and also the proportions of the image is maintained. So here, like, instead of having like 3 cameras looking into different directions, we are having one wide angle camera looking in the front and keeping all the details and proportions of the objects. Here is 2 images captured by the same camera in the room where I'm sitting now. So here is actually the camera and the lens, and we, on the left image, we applied the distortion correction, and on the right, it's just original image. You can see the results. So quite impressive. And here you can see the distortion correction applied videos with Immervision lens and on the chip hardware accelerated distortion. And the next slide is augmentation and distortion applied at the same time to see both of our developments in action. So these are the 2 topics which I wanted to highlight today. Thank you very much. And let's go to the questions and answers. Also, I'd like to say great thanks to the people from On Semiconductor, Immervision, and SIVA for helping to bring up this solution. And let's go to the questions and answers. Thank you very much.